Another interesting application is called Hall effect. Hall effect is, the idea of Hall effect is, say, I have an ion, right? And we know that an ion is so small. So if you want to make this ion move in a certain speed, how can you control that, right? It's not a baseball that you can just hit it. It's an ion, which is so small. How do you accelerate an ion or control the speed to a point that you want? How do you do that? So the way to do it is we call it Hall effect. Hall effect, the idea of a Hall effect is to use the magnetic field and electric field to control the speed of a particle, a charged particle specifically. So how does that work? So first, we can send in an ion inside with whatever speed, I don't care. It could be any kind of speed. And then I will send this particle. So this is my particle. Now I send this particle into a uniform magnetic field. It could be created by 2-bar magnet or electromagnet, whatever. But basically, you want to send this particle into a uniform magnetic field, which is denoted by this orange. Okay. And then on top of this uniform magnetic field, I also apply the uniform electric field across the system. So you can see I put 2 parallel plates here. And because I have 2 parallel plates, so it's gonna create electric field line, a uniform electric field inside this plate, between these 2 plates. So now now you can see my charged particle will feel both the magnetic field and electric field. So now let's look at the electric field first. The charge feel the electric field, then we'll create an electric field force. And if you look at the direction, because this is positive, so it wants to go upward along the field line. So first, this guy, if I draw the free body diagram, you can see my particle will feel electric force going upward. And then because it's a moving charge, so it's gonna feel the magnetic force as well. So this moving charge will feel the magnetic field and then cause it and get a magnetic force. The magnitude is just QVB. And how about direction? To figure out the direction you want to use your right hand rule for the force. So this is V, this is B, and this will be your force. So now try to align your force, align your fingers to pointing at the direction here. So you can see the speed is going to the right. So your second finger should go to the right. My right is this, but it's going to the right. And my field is out of page. So you can see that my force is going downward. So my force is going downward. Okay. So the magnetic force is downward. So in total, if I send a charge here, this charge are going to feel this 2 force. All right. So if somehow we can control, because this magnetic field and electric field is something we put in, right? So we can control, there's a knob where you can control the strength of them. So if I can control this field and this 2 field in a way that the charge is traveling in a straight line. It's traveling in a straight line like this, okay? It's not bending upward or bending downward. It's just traveling straight in the straight line with the constant speed. If that happens, it means this particle experience a force equilibrium. Like the net force acting on this particle should be 0. So this equals to that. The net force is 0. If electric force is magnetic force, they cancel out each other. Then I know Fe is QE, Fm is QVB. Then this Q can cancel out. and then I can move this B over to the left, then I get a speed equals to E over B. So you see, what's the speed? This is how you can control the speed of ion. As long as you put in a certain electric field, which is something you can control, you can put in the magnetic field, which is another thing you can control. When you put them in, then you can guarantee the ion, the speed of the ion is gonna be its ratio. So it's really a cool thing that you don't need to touch anything that's like, you know, such a small thing. You can just by putting this playing with this two field to control that speed. So the next application I want to introduce you is called mass spectrometer. So this is a very useful device when you want to, for example, if you have a collection of oxygen, but you want to find how many, what's the isotope distribution, you can do that. So for example, if I send out a lot of ions, some of them are oxygen 18, some of them are oxygen 16. So they carry different mass, but assuming they carry the same charge. Now I send this ion into this Hall effect. Then I can basically control the speed of these ions. So both of these ions, they will have the speed of B equals to E over B, right? And now you can see this, both of these ions will come out into this uniform magnetic field area. And in this uniform magnetic field area, you can see that the only force experienced by this charge is just magnetic force, which is QVB. It's not canceled out by anyone or any other forces. So this force, because, so let's take a look. If my charge is, so oxygen is usually negative. So my particle is going this way, and the picture here is positive, so this is not a very good example. All right, let's assume, I know this is not true, but let's assume in these two ions, they're positive. So assuming it's positive, and this velocity going to the right, magnetic field is out of page. So if you use the right-hand rule, you can see that the direction, the magnetic force direction at this point will be downward. So this magnetic force, QVB, will be downward, which means it's perpendicular to the velocity. So it's gonna make this particle go a circular motion to change the direction of this, this particle. So the centripetal force is the force which can make a circular motion. And the relation goes like this. Centrifugal force can make a circular motion with a certain speed and certain radius. Okay, so now let's combine these two. Magnetic force provides the centripetal force. Okay, so now we can move things around. Let's move R over, move QVB to the right. Then let's see, mass of them will be different, okay? But we know that the speed is the same because the speed is controlled by Hall effect before it comes in. Charge is the same for both ions. The speed, again, is the same. Magnetic field they experienced is controlled by the researchers, so which is the same. Therefore, you can imagine this oxygen 18 because it has more mass, it has a greater mass, so its radius will be greater. So if you see a lot of ions here and only see a little bit ion here, that means your oxygen 18, you have more oxygen 18 than oxygen 16 in your ion source. Okay. Basically, the idea is magnetic force will make a particle turn, will make a particle turn like a circular motion. And because of that, if your particle has different mass, then you're turning the circle, the radius will be different as well. So just by utilizing this simple idea, we can use this device to separate our ions of different masses. Another similar interesting application is we call CRT. This is the very first prototype of our television. So like you remember that before our television was like huge box, and that is because to make a CRT you do take a lot of space to make it happen. So this is what in one of the discussion session, it basically described the principle of a CRT television. So here I'm just gonna review a little bit. A CRT television, what it does is that it has a collection of electrons, and then it uses some electric field here to accelerate the electron. So the electrons will come out straight in this way. And when the electron come out in this way, we can apply some current here. For example, I can connect it to, say, a battery. Plus and negative. And when I apply this battery, say if we can control the if we can control the voltage, then which means I can control the electric field here in this little area. If I can control the electric field here, then I can basically control the motion of my particle. If my field is going upward, then my particle will want to bend downward because it's electrons. And if my field is the other way, it will bend upward. So basically I can control these electrons up and down. So say if I control this electron up and down, so say the first electron will end up to be here. Will end up to be here. The second electron end up to be here. Third, fourth, so on and so forth. My electron will eventually will go this way. So basically, if you control your current well, you control your voltage well, you can actually bend your electron and make it goes like a dot like this. And if you're going fast enough, your eye will feel like it's a 3, like this. All the dots which composed of this number show up simultaneously on the TV. All right. So this is 3. Another way to control electrons is by magnetic field. You can also use tune the magnetic field to make your particle turn. And when you make your electrons turn, you can use control the electron and make the electron go to wherever you want them to go to. All right. So this leads to a very important question that people care about when they're still using the traditional CRT television. That is, if you have a CRT television, your parents, if you had one before, then your parents will probably tell you, do not bring any magnet or current near that TV. And in the following, I'll show you a video and you'll see why. So what you're seeing here is a very big CRT. It's a vacuum chamber. The electrons is coming out from this end. And when the electrons come out from this end, so this green light, you see that this green light is an electron beam. All right. And now Vasek will put a magnet, a horseshoe magnet around this electron beam, and you'll see what happened. So you see, if I put this, now if Vasek, you see like this horseshoe magnet is going this way, where this end is north, the other end is south. So this end is north, this end is south, and it will bend out my electron beam downward, right? And what if now we switch the polarity of this horseshoe magnet? Okay, if we switch it, then you can see it will bend upward. Right. So this is, you can see how to, so now you can see how to use the magnet, electron magnet to control the beam of the electron beam. So this is a television. Okay, this is an old style big television. And this old style big television, if you open it up, you will see a lot of the CRT tube that I just showed you in the previous video. And those CRT tube, they have three colors: red, green, and blue. And these three colors can compose of any other colors in the spectrum, as we talk about in the optical wave. So usually you can use this to watch a TV, but you don't want to put a magnet around your CRT TV, your CRT television, because if you do that, this is what you'll see.
Magnet. And this is the CRT TV screen. And watch what happens when I put it close to it. You can see red, green, and blue color patterns.
So this is what would happen if you put a magnet near this CRT. Because this is a strong magnet, it's gonna distort the motion of the electron beams in your television. And when that happens, those electrons will just go everywhere and just go randomly everywhere and form this funny pattern.
When I put it even closer, you can even see the menu bar being distorted.
So the original signal will be somewhat washed away because of this, because the effect of this external magnetic field.